I wanted to do an example of a problem from 2.3. Typically in your homework in 2.3, you're asked to find all rational zeros of the polynomial function. In the next section, you'll be asked to find all zeros, including complex or irrational zeros. Let's see. So in this problem, we're asked to find zeros of this polynomial function, 2x cubed plus x squared minus 13x plus 6. So the next thing to do is to use the theorem in this section that helps you find all of the possible rational zeros of a polynomial. So you might have read that the possible rational zeros have the form all of the factors of the constant term over all the factors of the leading coefficient. The constant term in this polynomial is 6, so we want all the factors of 6 over all of the factors of the leading coefficient 2. I've written the factors of 6 here over the factors of 2. So now I just need to write all the possible values this gives us. So the way I usually do this is I'll pick one number for the denominator and go down the list. So if the denominator is 1, that gives us the values 1 over 1, 2 over 1, 3 over 1, 6 over 1. So 1, 2, 3, and 6. If the denominator is 2, you get 1/2. 2 over 2 is 1. We already listed that, so that's fine. 3 over 2. And 6 over 2 is 3, which is already listed, so we don't need to write that again. Alright, so here's our list of possible rational zeros. Now you can look at that list and maybe you have an instinct where you think that one of these numbers is going to work and you want to start with that. Otherwise, you just go down the list. So if I evaluate f of 1, let's see, that's going to give us 2 times 1 cubed is 1, 1 squared is 1, 13 times 1 plus 6. This isn't 0, so we need to move on. If I plug in -1, let's see, that's 2 times, so again, I'm substituting into this function up here. 2 times -1 cubed is -1, plus -1 squared would be +1, minus 13 times -1 plus 6. Well, let's see, that's -2 plus 1 plus 13 plus 6. That's not going to give us 0. Okay, so moving on down the list, f of 2. 2 times 2 cubed would be 8, plus 2 squared would be 4, minus 13 times 2 plus 6. Well, let's see, that would be 16, plus 4 would give us 20, minus 13 times 2 is 26, so 20 minus 26 is -6, plus 6 would give us 0. Okay, so we found a 0 of the polynomial. Now where do we go from there? Well, there is another option to just continuing down the list and plugging everything else in. That's not the most efficient way to do this. Once you find a 0, you should take advantage of the factor theorem, which says, I can get it written down fast enough, if you have this polynomial p of x, if c is a 0 of the polynomial p of x, saying that c is a 0 of a polynomial is equivalent to saying x minus c is a factor of the polynomial p of x. I'm abbreviating it here, but you've seen this in the study guide for 2.3 and then the textbook, so you guys can read through the exact statement of the factor theorem. But the basic idea is that c is a 0 of a polynomial if and only if x minus c is a factor. So that if and only if phrase means that the logic goes both ways. If x minus c is a factor, then we can assume that c is a 0. If c is a 0, we can assume that x minus c is a factor. Okay, so we just determined that 2 is a 0 of this polynomial. So that means by the factor theorem, x minus 2 is a factor of this polynomial f of x. That means it should divide out evenly. The next thing you want to do is factor out this x minus 2. That way you sort of chip away at your polynomial f of x. As soon as you find a 0, factor out x minus that 0. That'll give you a polynomial of degree 1 less. And you can keep finding zeros and chipping away until you have a polynomial that's simple enough that you could just solve by inspection. Okay, so x minus 2 is a factor. We would like to now divide out, we want to factor out x minus 2. One way to do that is to take your f of x, 2x cubed plus x squared minus 13x plus 6, and divide out that factor x minus 2. And you guys have a nice, easy way to do that using synthetic division. So that's what I want to do now. I realized that you could also, instead of evaluating f at these values, you could use synthetic division and the remainder theorem to evaluate f at each of these values. For plugging in things like 1, I prefer to just plug them in. I think that's quicker than using synthetic division, but that's up to you. Okay, so I'm going to perform this division using synthetic division. So I'm going to put the 2 here, and I'll put the coefficients of the polynomial. The camera's rocking a little bit, sorry. Right there. Skip a line and draw a line. Bring down that first coefficient. Now you multiply 2 times 2 gives you 4. Add up these numbers, so 5. Now you multiply 2 times 5 gives you 10. Add up these numbers, negative 3. Now you multiply 2 times negative 3 gives you negative 6. Add up these numbers, and this last number here is your remainder. And we better get a remainder of 0. If x minus 2 is a factor, it should divide out evenly with no remainder. So this 0 is good. It shows that we're on the right track. It also shows that when we divide the polynomial by x minus 2, we get, okay, first coefficient is 2. Now we had x cubed, we divided out 1 power of x, so now we're left with x squared plus 5x to the first minus 3. Okay, so this is what I mean by chipping away at the polynomial. We found 1, 0, x equals 2. Now we're left with this polynomial, and this is one you could actually solve by factoring. So let me see if I can hurry up and finish this problem for you. Okay, so using this division here, we determined that if we factor out x minus 2, we're left with this, 2x squared plus 5x minus 3. Now if you remember your factoring, that can be factored as 2x minus 1, x plus 3. Now, setting each factor equal to 0, x minus 2 equals 0, then x equals 2. 2x minus 1 equals 0, then x equals 1/2. And x plus 3 equals 0, then x equals negative 3. So the zeros of the polynomial are 2, 1/2, and negative 3. They happen to all be rational for this function. One last little note before I go here. Notice that the polynomial that we started with had degree 3. Our polynomial was degree 3. And remember, you might have seen a theorem that said the maximum number of zeros for a polynomial is equal to its degree. So if this has degree 3, the maximum number of zeros is 3. So it's not a surprise that we found 3 solutions here. If this was a degree 4 polynomial, we might expect 4 solutions. At most 4 solutions. Occasionally one of those solutions repeats, so you only have 3.